Hello, my name is Abdullah Karar. I'm a research scientist with OptiWave, and today I will be discussing the modeling of laser RIN suppression using balanced photodiodes in OptiSystem. This is part one of a two-part series. Today we'll be attempting to validate a fairly simple experimental setup for relative intensity noise suppression with balanced photodetectors. A laser source produces light exhibiting RIN, which is split using a coupler and fed into a pair of balanced photodetectors with the resulting RF current indicative of the amount of RIN suppression with balanced detection. We will be examining two types of laser sources in simulation. The first laser source is a DFB laser modeled as an ideal single-mode laser, and the second is a CW laser measured component where the RIN could be set directly. So the details of the experimental setup could be found in the reference provided below. And it simply has a bias control for a DFB laser at 1550 nanometers, a variable optical coupler, followed by balanced photodetection. And through changing the coupling ratio, they're able to measure the RF signal for single-ended detection and for balanced detection. And just to observe their final experimental results, we can see here that using the RF spectrum analyzer, they can assess how much RIN is in this light source. And observing the single-ended photodetector case, there is a peak around 5 gigahertz in this particular case. Now, this peak actually results from the natural relaxation oscillations of the laser where the relative intensity noise is set to be maximum. And as you can see, successful suppression is obtained with the balanced photodetector case, and you can see that there is suppression in the RIN at that particular frequency. And the maximum benefit of RIN cancellation occurs at a specific frequency which aligns well with the relaxation oscillations of the DFB laser at that particular bias point. It is fairly simple to model the previous experimental setup in OptiSystem. And here we have a DFB laser modeled as an ideal single-mode laser where there is no input modulation and the bias is set from inside the component. In this particular case, the default threshold current is 33 milliamps. We'll be operating at around 66 milliamps, so this is twice the threshold current. And we can observe the RF power after photodetection at 2 points using a dual-port RF spectrum analyzer, one for the single-ended detection and the other after the subtraction, which is representative of the balanced photodetection case. And the results is shown on the right-hand side, and you can see here that indeed the single-ended photodetection has a peak that is congruent with the natural relaxation oscillations, and resonance is inside the rate equations of the DFB laser. With balanced photodetection, RIN suppression is achieved. And some slight variations on the previous simulation, we can, for example, allow the bias current to be much closer to the threshold current, and this results in the peak of this RIN coming closer to the vicinity of the DC and exhibiting a higher amount of RIN noise. And this is certainly expected when you're biasing a DFB laser under this configuration. Now, in this particular simulation, we're repeating again. However, we're replacing the DFB laser source with a CW measured source. And this particular component allows us the opportunity to set the RIN directly. For example, here it's set at minus 130 dBs per hertz. If you run the simulation with the default settings, unfortunately, as you can see on the right-hand side, the balanced photodetection did not work, and the subtraction did not result in a suppression of the RIN noise. And there is a reason for this. This is due to the fact that the PIN photodiodes under default settings have a particular property as per the documentation. And in the documentation, it states that if noise bins are detected at the input, they are converted into white Gaussian noise, which means that the arms after photodetection have noise terms that are decorrelated. And this does not help when we are attempting to perform RIN suppression, where we would like the noise to remain correlated after photodetection. The solution to this particular problem is to enable convert noise bins inside the DFB laser component. And in this case, the output of the laser produces the signal and the noise added together. in a similar way to the RIN suppression in the previous example, where the DFB laser had the RIN inherent in the output of the rate equations. So in this particular case, if we add the signal to noise produced at the output of the CW laser, this is enabled through the convert noise bins check. We obtain the expected RIN suppression in relative where the balanced photodetection is significantly lower than the single-ended photodetection. This concludes our short presentation. Thank you very much for your attention. If you have any questions, feel free to reach out.